Good evening. It's so nice to see a large turnout for .NETers. It's normally Javas and PHPers and everyone else, actually. It's really, really nice to see. So this is going to be a really, really flash and quick chat about multi-threading and trying to take a little bit more advantage of the hardware that we have available to us these days. So we're going to try and go through some of the multi-threading options that are available in .NET, understand a little bit more about how some of them actually work and what they do behind the scenes to make your life simpler in terms of the coding that they put forward. A few examples, and then we also, as you really should know, is with any good tool you look at the pros and you also look at the cons. And there are no ways of escaping it. There are cons as well as pros in this, so you may need to know alternatives. There are very useful alternatives if you need to get knee-deep and nitty-gritty and or want to really try and squeeze that little bit more performance out of the hardware that you're running on. And then hopefully I'll run a little example there towards the end again, and then we can have a quick chat. Probably best to save any questions till the end because I've only got about a 30-minute time slot and I'm not quite sure how long it's going to take. We'll see how we go. We are probably at a period in time where we are extremely fortunate. We've probably never had the capability in the past as easily as we do today to pick and choose the resources on which we want our application to run. In the past, you used to have to provision and buy a server that used to come in and physically sit in an office, and you have to do as much as you could with the resource that you've got there. Nowadays, we're extremely lucky. My desktop is a beast, and I run most of my servers as virtual servers on the desktop whilst my development environment sits there as well. But I've got that capability to fire up machines of whatever size I want within the boundaries of the resources I've got. And if we want to expand that further, cloud services are really cheap for developers. If I want to fire up a really beastly box out in the web and use it for 2 hours, it costs peanuts. You know, it's a couple of quid. Really not a big deal, but you can pick and choose the size of the machine that you need these days. With the likes of AWS and Azure and all of the cloud services, you get different types of machine instances as well. So you get the general compute instances and you also get memory optimized instances. So you can do a mix of whatever is suitable for your needs. Multi-threading, of course, can help us take advantage of multi-CPU environments and things that we have nowadays. And if you're firing up this resource and you are running it, you want to max it out as much as you possibly can and take as best the advantage you can of that resource and then turn it off as quickly as possible. So you're not incurring costs. Often people do fire up instances and they leave them running because they need a set minimum spec, but often that machine just sits there doing next to nothing. You know, this is where AWS Spot instances and other such facilities are the ability for that owner to rent out that spare capacity to other people as well. But it's really handy if you get the opportunity to look at the way you design your code and to try and isolate and compartmentalize the operations that you're performing to try and take advantage of them as best you can. So in .NET, we actually have 4 different options for integrating with multi-threaded environments. We have the traditional thread class, which was created and you can manage yourself and do things with, but the downsides with it are you have to create it, manage it yourself and do things with it. You've got the ThreadPool, which came along a little bit later. And that provided a mechanism for it to create and manage the threads for you and you to just allocate a function or a procedure that you wanted run, get it done and come back with the result. More recently, this has evolved into the task parallel library and parallel link, which offer 2 very much easier ways to offload a particular function or action that you want done to get a result back in short amounts of code. Now, with the 2 new options, the TPL and parallel link, which are the preferred options that Microsoft recommends now, they actually do use the thread pool behind the scenes. So they achieve most of their work by sitting on top of an existing architecture that sits there anyway. So the thread pool actually is very important, or should I rephrase that? Thread pools are very important. Threads, as you probably see here on the screen, I just pulled something up from the Microsoft documentation. It says here, both TPL and P-Link rely on the thread pool threads, okay? So it's important to understand that and just to get an understanding of what that can do and the limitations and capabilities of the thread pool underlying it all. Oh, seems to have gone backwards. Okay, so the ThreadPool class itself is, and I won't go through these in any particular order, it is a static and also sealed class provided by Microsoft. You can queue up functions that you want to occur via a call to queue user work item, and provide it your procedure or your function that wants to be called, it will queue it up with the appropriate threads and run them as and when it can. It does provide a wait facility, but it's generally per item, so you then have to provide that every thread or action that you want set up, you have to queue up with the wait options. It allows you the opportunity via a number of methods to get the size of the minimum and the maximum threads, and also to set them. Though, as per Microsoft's normal standard documentation, they say pretty much leave this alone, and we do it all ourselves, leave it be. One thing it doesn't do by default is it doesn't provide you a facility to choose the thread priority. Because with the .NET framework, we of course are running on top of an operating system. We are not actually controlling the threads of the operating system and the priority that they get allocated in the appropriate OS. So any of those that have done multi-threading before on the operating system level or .NET, okay? So there are various different degrees, and most threads start at the normal priority, which is evenly shared across all processes that are currently running. There is a below normal, there is a low, there's a lowest, there's also an above normal and a high, okay, priority. Ideally, you don't want to allocate too many threads that are high. They generally starve the rest of the operating system or programs with CPU time. So normally, and as is the default in this case, Microsoft instantiate it as normal and leave it at that. They assume that they are trying to make your life simpler for multi-threading, so therefore just leave it to it. That in itself can sometimes cause problems. You may have issues that you need to do that require a bit more finesse or a bit more control, because at the end of the day, we human beings solve the problem. The machine is just a tool to help us do it. Sometimes that problem isn't just straightforward. It's multi-steps perhaps. The downside with it, it's not abstracted out, it's not an interface, it's a static sealed class that you interact with. And it also is non-instantiable, so you can't have more than one. So what it does is that does actually make life very simple for most people in terms of getting into multi-threaded. The approaches now are very much reduced lines of code to actually achieve a task without too much effort. However, I will rephrase that as actually simple tasks. Try and consider it a simple task. If you get complex tasks, I'll talk about those a little bit later, you should try to split it up into separate operations. Okay, so we're going to have a quick look at some of the Microsoft examples. Right, we might have to pause that then. Not visible? Right, okay, thank you very much. And then the cursor disappears. Right, can we all see that? Is it readable? Roughly? A little bit bigger, a little bit smaller? Guys at the back? No, I'm just driven by you. Shock over your desktop. In shock over my desktop? Oh. You haven't seen the other three monitors. Yeah. Well, these are all just Microsoft examples, hence the giant, great big logo and multicolored code we've got here to have a look at. Okay. So what I've done, and I'll provide the examples across for Paul for download, but they're just taken from the Microsoft site in this case, is I've tried to chain 3 or 4 of them together, all of which just do something. So I'll just run it very, very quickly, run through it, then we'll take a look at the examples as to what they're doing. I say quickly. I mean whenever my machine really wants to. Okay, so this one's just run a quick task saying hello. Another one's run a few things, manipulated a few images. That one's run a bunch of things. That one's done a huge amount of maths. And that one's doing lots and lots of things, as you can see. Okay, so let's take a quick look at some of those. I'm still getting used to the keyboard and the function keys not working quite as you like. Okay, so this is the approach to create a single task via the task parallel library. Very simple. In this particular case, you're defining a task. You can instantiate via the call to run and schedule a action, in this case just a link statement, straight in to a very simple call to console write line. Okay, that is actually then pushed out to the queue, does something. As you can see, we write something else out saying hello from so-and-so, and then we just wait for the thread to complete. Very simple, not very difficult, but actually that is actually doing this in a separate thread if a separate thread is required. It doesn't necessarily mean you'll get something off the main thread if the task isn't hard enough for the processor. So the next one along is scheduling a task that returns a value. You might want to actually action something after you've done some work, perform something, get a result, do something else with it. So in this case, you take a very similar approach. You again start at the task class. In this case, we're defining with the use of a generic that we want a task that returns an int. And we call the factory start new and give it something. In this case, again, it's a very simple effort. It's just passing one back as a return result. In this case, you then get your task and you call .result. You can get the result from the task that has been actioned. But that's been pushed off, come back to you. You've done very little effort and very little lines of code to actually achieve the result that you're after.
How do you know when it's finished so you can get the result?
It will come back to you right there at that point. Well, in this case, obviously it's a very, very quick and simple one. I'm glad you actually brought that up, because in the attempt to call result here, if the task or the thread has failed, trying to access result will result in an exception. There is actually another property on your thread is completed that you can check to see whether or not the actual thread completed without error behind the scenes, okay, which you really, really can't see. Okay.
Is there a difference between using the await keywords and calling .result?
So you're talking async await? Okay, those are slightly different. You're talking about asynchronous programming there, which gives the illusion that it's multi-threaded, but it isn't necessarily. In fact, in most cases, async await actually just allows asynchronous programming to allow that code to execute, and generally, in most cases, it actually executes on the same thread. So generally, it actually executes on the same thread until it completes and then continues as it was. So asynchronous doesn't necessarily mean threaded programming, but it can be sometimes. Depends on the way the person has used it, unfortunately. However, the important thing here is the factory, which allows you to gain access to the method called start new, which allows you to schedule a task. You can also create a task yourself, populate a bunch of properties, parameters, and so on, and pass it into that start new. Okay. In this case, we've just got two tasks that happen here. They both return some kind of result, and then it comes back. The next is an option which shows the crossover into parallel link. So you may be used to using link statements to access arrays or lists and collections of items. In this particular case, the only difference here is the addition of, and I'm sorry if it's small there, let's see if we can magnify that a little bit. Okay, is that any better? So you've got this afterthought to your collection called as parallel, which what this will do is execute this entire link statement as a multi-threaded element. Okay, so it'll queue up all the items that are in the collection into whatever the statement is you're preparing or wanting to action, and run those in parallel if at all possible. I say if at all possible because it chooses whether or not it's possible to actually run these in multiple threads in a thread pool, or if it comes back and runs them all on the same thread. It depends potentially sometimes if you're having any kind of concurrency that's involved. I'm running over concurrency in this case with threading because it's a very big topic, and we've got half an hour and I'm probably running a little bit behind as it is.
It's no good time to point out you've got 45 minutes.
You said half an hour. Yes, you did. Okay, right. Which leads on to, as I mentioned a moment ago, the task factory. So here's another option showing, in this case, where you are passing in a parameter to the function. So the function that's being executed can receive an object. In this case, you can do something with the object in that they're casting it to a custom data object, and then they're actually performing any work on it. In this case, it's very simple. We're actually simply just getting the current thread ID, and if we're going to set that back to the parameter thread number on that data instance, and that will be returned back as a result from this task. Yep, and it's scheduling it into a task array. So what it's doing is it's creating a task instance, and it's giving you back the result of the task object, which you're adding to an array here. And at the bottom, you'll notice that there's a line that says task await all, and that's passing in the collection of the array of tasks that you want to wait until completed. Okay, so at this point in time, the task parallel library goes off, it's creating all these tasks, scheduling them all up, and then it's allowing you to call that one method to say, I want to wait until all of these are finished, then I'm going to do something with the results. Okay, so again, it's actually very, very short code compared to the ways, you know, if any of you actually fiddled with the thread class and trying to do it the hard way in the good old days, it's, you know, I've got twice as much code as that just to get set up and started. These nowadays is very much simpler and easier to cope with. The downside with all of these things that are made nice and simple for us is it takes an awful lot of control and flexibility away from us as well. We can't control the thread priority, so we can't say I've got a certain number of tasks at really, really high priority, I need to get them done first, and then I want to do some other ones. Because you've only got one thread pool, you can't actually control in which order your item is going to be taken out. You may wish to say, okay, well, here's a situation. I've got items that need to be executed very, very quickly. Then I've got normal ones, which I don't mind too much about. And then I've got ones that have got long effort of time. Maybe they're calling a website, a web service, or they're doing a prolonged I/O operation. And you don't want those running on a high priority. So you get into a situation where potentially you've got a series of steps in your process to achieve the result that you're after. Maybe it's initial database operations, that's quick and simple, and maybe you then do some analysis with it, maybe you then write out that data somewhere else or pass it on to something else. So potentially you might need to segregate those things into multiple steps and do something with them. So how do we do that? In the case of the task parallel library, we actually have a method that is available, which you can't actually see on the screen there. Yes, you can, sorry. Called continue with. Let me see if I can make that just a little bit bigger. Is that any better?
Yep.
Yep. Okay, so we take a similar approach again. You call the task and there we go. Call the task factory to queue your new task waiting to be done. And with the result that comes back, you can call continue with as almost a way to say, okay, I'm going to extend the result of this thread and the work that it's performed. If it completes correctly, I want you to then do this. And that will also schedule another task into the queue to be completed later. In this case, we perform a huge bunch of very basic operations, grabbing random numbers, putting them into results at the back, and then we do a sum on those in a single thread in this case, because all it's doing is taking a whole bunch of data, processing it, and giving you back one number. So it's not likely to be creating more than one task there. But again, you've waited for the initial tasks to be complete, then performed secondary work on it. Okay, and that again is all in a single page that we can see at 200% view. So it's really quite simple to look at. Now, parallel link takes a slightly different twist, but it does make some methods very much easier where you have existing code that has a for or for each type loop. In many of those cases, you'll find that the parallel link provides what am I thinking? You'll find that there are actually methods on your collections that are called for and parallel for, as well as parallel on a collection for use in the link statement. Let me just see, so we've got a number of queries there. Actually, yep, that's where we're going to. Okay, so your parallel class also has a number of basic operations on it, so you probably can't read those, unfortunately. A for, a generic for, and a for each, which allows you to action the tasks that you're then going to define in your code, which you already probably had defined in your for loop somewhere, to be executed in parallel, if at all possible. Again, we come back to this situation where it determines whether or not it's possible to run it as a multi-threaded operation. So the common one that would likely be used by most people would be a for each with a generic type, and then your code would action after that. So you've reduced a lot of that threading work down to, again, a single line of code. So it's really, really simple and easy to operate with if you have basic operations that need to be performed. And you see with the use of the parallel link, you can make your normal link statements multi-threaded in cases where you're operating on collections just by simply adding the as parallel method call after it.
Which would be the main thread waits for it to complete?
Yes, in those cases it runs all items, and the parallel for has an advantage of a built-in wait where your task parallel library doesn't. You need to specifically call to wait for something. The parallel for does the wait for you embedded in there. So in these operations, it will do all the code, it'll execute all the tasks, and it will wait in there for it to return and then bring back to your code. Which in this case does nothing particularly exciting, but write out what line it is, what managed its thread ID, and whatever number it was passed in. Okay? So we just get back to where we were. So about 15 minutes?
25.
Oh, okay. So, understanding the limitations of these tools is the next important thing. We, as people, have problems to solve. It's great to solve them, but we then need to see how we have a problem with the tool that we've got and how we try and get around that. So both the task parallel library and the parallel link use a thread pool behind the scenes, so we can set the threads, minimum number of starter threads, the maximum number of threads that it can run, and we can queue items, but we can't control thread priorities. Okay. So the default thread pool implementation also allows only one instance because it's static sealed. So if we have a situation where we want multiple pools for a specific reason, we can't do that. A classic example I was given was by someone for a web crawler. A web crawler might not want to overload a particular website with more than 2 or 3 requests at a time, but it might want to be crawling lots of different websites at the same time. So one of the easiest options for that is to have multiple thread pools that you can schedule your threads in and the calls to all the pages that you want, but you can't do that here because you can only call the one thread pool and queue items up. So that's a limitation again.
So is this more like sort of MSMQ, Microsoft Message Queue?
It's a very simplified way to introduce programmers to threading.
Right.
It's a way to take away a lot of the grunt work if they use it with very simplistic operations.
Right.
And for simple actions. If you were to pass, say, an item in a collection straight into a very complicated routine, that would generally be a bad thing for different reasons, but would be a bad thing. The issue I had in the past often was that often you find that when you're doing the business tasks, you have a need for different priorities. You have a need for different items to be run in a different way, or even different steps of the same process to perform different things. Some that might be very random I/O, high random I/O, writing out very large data files. You don't want that to be on a high priority thread blocking the rest of the system's operation. Likewise, you don't want too many threads running at the same time doing heavy I/O operations because they're just going to slow down everything else. So actually you need to stop and think, okay, what's my application doing? I know that better than the machine, so let's break it down into the tasks that we need to isolate and to action. Again, that leads to whether or not we're able to action out and allocate different tasks to different items. So as soon as the ThreadPool was created by Microsoft, everyone started pointing out these flaws, and of course, as a byproduct, everyone created their own instead. So there are wonderful alternatives out there, and there's a really good article written by Amy V actually here, and she wrote a very, very good article many years back now. I think I've been using this ThreadPool for about, I don't know, 8-10 years, and it's an excellent tool. It's now on GitHub. It hasn't changed in about 4 years, but it's had no real need to do so either. So it's static, it's old. Some of the methods are not as generic as possible because she originally wrote it to be .NET 2 friendly as well as Silverlight and Windows Phone. Well, they've gone away, so not so much of a problem anymore. But it is a very, very good tool. Okay, so what does this provide? This actually provides us a means to create instances of our ThreadPool. So we can instantiate as many instances of the ThreadPool as we need. Say we have a beast of a machine and we've got multiple processes running on there. Each one might require a ThreadPool, but you might not want to max out the entire machine for that one process because you know this other process is doing something. Each of them can have their own ThreadPools. Or alternatively, in the instance of, say, the web crawler or some other similar situation where you may need to control the number of threads performing tasks, you can also do that by creating more than one instance yourselves. Because of the way it was written, it was deliberately written to allow you greater control of the way that you can operate the threads in your pool. So you can actually create groups in a single thread pool, and inside each group you can allocate threads. So if you want a task to occur in a thread pool that's a high priority item, perhaps it's a very quick random memory access or calculation, you can allocate that into one group. You can pile that group up and load it up with a different number of threads that can run concurrently to another group that might be doing database operations or another group that's doing I/O operations. So instantly the thread pool starts to become the controller here and actually allows you to allocate things in the groups that you want with different priorities, and the thread pool will allow control over priorities on two forms. It will allow you just a simple priority element within the thread pool itself, or it will allow you to actually control the thread priority of the threads created in that worker group. So it can manage those for you as well. This is a very handy feature because you can create as many groups as you need to segregate out the work that you want to do, allow a task to run on one thread pool. Once you've got a result back from it, potentially you can add it into another worker group and get it to continue the next step in the process. And each one is configured differently, but you're allowed to control those. So it's very, very handy. The work items are abstracted interfaces. So a lot of the code is actually moved down to an interface level, which is great. You know, it's nicer to be able to swap interfaces in and out. If you want to override something that currently she has in a default, you can go off and write your own element to it. Like I say, it's an older project. It's about 4 years since it's had a change, but it's still very, very handy. Okay, so back to some other examples quickly. If the cursor doesn't disappear, sorry to say. Okay, now I just need to make sure that we've got a couple of things running here. We're not on a network, go away. Okay. So this demonstration allows you to have a look at some of those features that we talked about, whereby we can create not only a thread pool, but a number of groups to allocate perhaps and differentiate the threads that we want, or the tasks that we want running in this case. So it's a very small one, isn't it? Let me just up the view a little bit, sorry. So, is that any better? Readable at the back? Okay. So in this particular case, what we're going to do is we're actually going to use the advanced features because we want to talk about these groups, because I find these groups invaluable, and I think in many cases most people will realize you've got more than one situation you need to do something within a company. So in your code, we can create these groups, and the groups down here I've created red as the high priority items, green as the normal, and blue as the low. So these will be operated on differently by the ThreadPool. So what we'll do is we'll just queue up a bunch of items quickly. And all of them are just going to have slightly different operation times. So let me just queue some in there that are 2 seconds. Okay, so we've got a whole bunch of items queued up, and we can just start and stop the ThreadPool as we require. Now at the moment, we've set the concurrency for each of these work groups to just 1 item, and the ThreadPool to a total of 5. So you'll see at the moment we've just got 3 items running there, and if I move up, you see we're using very little of the actual machine. So I know in this particular case we can max that up to something like 20, and what we'll do is we'll start maxing up some of these, which are actually changing things dynamically in the background. So these are actually connected to elements, properties, on the actual work groups themselves. So they're actually interacting with those instances that are queued up. And you can see the ThreadPools are managing it all for us. We're maxed out on the CPU at the top now. And you can see from the color differential that we generally have a fair split of the items that we're looking at. So we've got 4 low priority items, we've got 10 greens, and we've got 6 high priority items, all being managed by the ThreadPool itself. It's knocking down the queues, as you see down the bottom here. The lowest number on each of the queues is the number of items that are currently running. Oh, I've forgot to actually shut down the generations. And you should see that those items in the queue will start depreciating and dropping off the scene. The red one's dropping off the scene far faster, generally, because it's queued up in the highest priority. All the items are kicking off in the background, and as you can see, we're just chewing through those numbers, but we're still maxing out the CPU. However, if we start dropping the available threads, the work groups, we can adjust the priority as needed, and we can see the corresponding result to the CPU. It's actually very quick, very easy, and we can interact with it. This is obviously a demo just to allow you to visualize some of those elements of the operation behind the scenes. But the power is very simple and very quick and easy to get access to. The downside generally comes with more code. So there's a lot more code to be written to allow you to be able to control those parts. But once you've created the instances of your work groups, you can just set properties on them to adjust the max and the minimum number of threads that are running in each of the work groups dynamically. So you can react to the load on your system if you choose to, and run more tasks if your system has spare capacity, or you can set a limit, say 3/4 of the tasks you know will max out the system, to allow other processes on the system to keep running. Maybe there's databases or there's some other operations that need to run, services or daemons that need to run on a regular basis. In this particular case, I just wanted to flick over to the resource manager as well and show that when we're actually maxing these items out, the effect of having, say, 20 threads in the effect of having 20 threads in the ThreadPool has actually come with a corresponding number of 35 threads for the actual process running on the operating system. Now this is a Windows application, so it's running on a Windows system. By default, there are about 13 threads that are running on your Windows Form your Windows Form application in .NET when you fire it up. So it's using about 22 actual physical threads on the operating system to manage the 22 managed threads in the .NET environment. Okay, so there's 1 or 2 probably hidden behind the scenes that are constantly switching out and returning the values that they've completed in the past. So I will just stop that up quickly and come to another tool very, very quickly that shows a whole bunch of login information. But the reason I've tried to log out into this tool in particular is to just give us a visualization of how much work certain threads are doing. So I'm just going to pick a few threads from the logs, because we can see a thread column here. So we've got 19, we've got number 9. And what it allows us to do is actually see the work being performed on that particular thread. So in this particular case, that's a managed thread that's running in the .NET environment, and you can see down the right-hand column there, everything is running for thread 19 in this particular case. But you'll see a mix of items that are actually running here, because the actual thread priority I didn't change the default on, it's still running as normal. You can see that's listed for all of them, regardless of what the priority was that we set for the work group. So for the work group I've highlighted there, that was a high, below it's a low, above it is a normal, but they're all running on the same physical .NET thread. The thread pool's just managing which one runs with a higher priority. You can, as I say, override those. So if you want to, you can go into the code and actually change the way that the thread groups and the thread pools are. Oh wow, with magnifier, that's really freaky. Excuse me. So with your thread pool, you can actually set some start information for both the pool and for any group instances that you create in the pool. So here, it provides an opportunity for you to actually, which of course when you're running in 64-bit doesn't let you do, excuse me. You have a couple of properties that allow you to define whether or not you're actually going to change the managed thread in the .NET environment, or whether or not you're going to change the work item priority, which is the smart thread pool's alternative to kind of a faked thread priority perhaps. And that was the mechanism it was using to define the high, normal and low operations that were running in the three groups that we had active. Okay. These same priorities and configuration information is passed to the creation of a new workgroup item, which, oh, sorry, still getting used to the old laptop here. The function keys, annoyingly, do something different. So the thread pool itself has the opportunity here to create a work group, which returns an interface to that work group for you. But you can pass in a variation of that start info that you pass to the thread pool. So you can create the thread pool initially with a certain piece of information, customize it a little bit to create the thread worker groups if you want, and then you can use those worker groups to actually call the same methods that you would on the thread pool to queue user work item and schedule up your items. Okay, and so this provides a very much more flexible option as a tool for your tool belt, but it requires a lot more code, and it requires you understanding how your application operates a bit more. It's not as reduced and concise as all of the options that Microsoft gives you, but it gives you a lot more power and flexibility as to how you wish it to execute once you have set it running. You can also start and stop it, which you can't do with the default thread pool. It will get active as soon as you give it something. It'll go off and do something for you. You can queue up as many items as you want into your instances of this, the thread pool or the worker group, and you can set the worker groups started individually, or you can start the thread pool and it will start any worker groups that are active by default. But you can pause worker groups by stopping them as well, so you can certainly take them out of contention if you want other tasks to activate and just take most of the resources thereafter. I'll just try and flick back to the last slides. Okay, so as we've probably discussed already, the interfaces are provided for many of the operations in this, which is a nicer opportunity for you. If you wish to replace some of the functionality, you can do so. It's all queued up on GitHub, so the source code's all there for you to be able to use and customize to your environment. It allows more control over the number of thread pools that you have running in your application or your environment as a whole. Queuing of the work items is actually much more flexible. The methods provide standard types where you can just pass a void procedure, or it allows you generic types where you can define a function or an action which may take one or more parameters into it and allow you to return a type from it as well. So you can actually get a workgroup result, and you can access the instance of the generic type that you want to return back to your code to actually do something with. There are a number of different methods that you can call to wait on the items, and you can wait on per group, or you can wait on the thread pool as a whole. So there are a number of options there for you to even determine or action groups, whether they have idle actions or idle activities. You can get events called to say that this group's idle, do you want to do something with it, or do you want to add more items to it? So it offers an awful lot more features than out of the box standard. Like I said, it is an older project. A lot of people would probably change bits of it or modernize it a fraction and reduce some of the code, but it works very well and it compiles into .NET 2, 3, 4 onwards, and I think there are even projects running on Core and Mono on it. So it's very flexible and you can use it in a lot of areas. Okay, so there are benefits to all types. The Microsoft approach, very much reduced code, parallel link and the task parallel library, all integrated already, very concise code, but it's very much designed for simplistic operations, okay? You can chain with things in the task parallel library with the continue with method, and it allows you to queue that code in order, but again, you really need to understand how these threads operate and the amount of work that a task is performing may need to be concise to be effective in a multi-threaded environment. If you have 100 items saving a 100 meg file to a hard drive and they're all blocking the thread pool, then your CPU is not going to max out, but your hard drive certainly will. So you need to understand the operation of your code as well as the task it's undertaking. No control over your thread priorities, but you do with the other options. So depending on what your needs are and how detailed the performance you wish to extract from your machine, you may be better off going with something like the Smart Thread Pool. If you have a team that aren't really familiar with threading at all, the first approach with the Microsoft one is probably the sensible one because it's a very simplistic approach and most of them can probably cope with that without needing to know much about concurrency. Once you start getting to the point where you start moving from that first environment of Microsoft and you want to start saving data into lists that are shared between all the threads, you start hitting environments for concurrency. You need to know about semaphores, mutexes, and other elements like those to allow you to share them. But there are advantages in that world in that Microsoft provide a number of synchronization synchronization classes for dictionaries and lists to allow your threads to interact and save data into items like that these days. In the past, you used to have to do that all manually, semaphores and mutexes to control entry and exit to save your data consistently. But there are a number of classes to help you do that now, if you need to get that far. Okay, that was a very fleetingly and quick visit into multi-threaded in .NET. I'm sorry about that. It is a big topic and there's a lot more to it, but hopefully those will be areas enough to get you either started or to give you something a bit more interesting to cut your teeth on a more complex project with and try and extract more from your resources. Hope that helps.
Got one weird question.
Sure.
It's strange. Given the fact you've got more and more cores on your processors nowadays, how does that interact with threading?
It depends on your processor and how you've configured it. If you have hyper-threading on the Intel processors, for example, turned on in the BIOS, you get 2 virtual cores to a physical core. If you have it turned off, you only see the single physical core. So in my desktop is a 6-core workstation, but it has 12 virtual cores. So I can queue up an awful lot of threads with the hyper-threading turned on. Turned off, those threads perform a little harder work, but less cores available to you. In most instances, especially in the clouds, you're dealing with virtual processors, so you don't actually see the physical ones underlying it all.
Okay. So is it actually worth turning it on?
It certainly can be. If you've got short, quick tasks, they're brilliant. If you have longer, complicated tasks that need to run as a sequential threaded task, you might be better off actually turning it off.
Okay.
That's to prevent the context switch.
That's Intel's way of trying to make the performance seamless in the hardware abstraction layer so that you don't have to worry about it in the software world. The processor does some clever stuff to allow you to have the virtual cores in a hyper-threaded environment, and if it doesn't, it turns some of that off. So it treats it as more like one big core rather than a smaller core. There are pros and cons to all of them. I generally tend to have hyper-threading on in most cases because most of the tasks these days, especially with the processors we've got, they complete very much quicker than they ever used to in the past. I had a situation where we were converting 120,000 Excel files on a regular basis, which is hideous when people start using Excel like a database. Just awful. But there's one other thing that's great with Excel is human beings. Despite you trying to lock down an Excel template or something like that, someone will always send it out unlocked at some point in time, and there are endless ways human beings can screw up a spreadsheet for you, which is great. So yeah, that 120,000 files, you had to be able to account for the errors, which ones didn't process, which ones failed where and why, so that we could get those items corrected. So the routine had to be able to run automatically regularly. And a lot of the I/O operations, converting some of that from Excel files into XML, and then processing the XML into a bigger XML, and then processing that all into a database was, yeah, great fun. But we managed to get it down to something like 6 minutes in the end for 120,000 files, so it's not bad.
Do you tend to bake this in like the first draft of your software, or do you tend to identify areas where this might be useful in future refactoring?
A bit of both. A bit of both, to be honest. If you know the tasks you're going to be doing are going to be either broken down into separate steps, and you're going to be performing lots of them, you can design it correctly from the beginning, so that it gives you that flexibility. You will often encounter programs that you have running that run a combination of database operations, some kind of calculations and maths on it, and or perhaps generating Excel files for people, because everyone likes Excel or spreadsheets or whatever else. And you might find that you've got an application that does this at the moment, but it's only using one core because everything's running on that single thread. You may be able to isolate those steps of the task and parallel it out to achieve the result very much quicker. So a combination, potentially, if you've got existing code, you might want to go the parallel link route, because you may have for each methods elsewhere, which actually could do that very quickly, and just swapping that out, you can get a big performance improvement.
Surely if you do it from the beginning, that's prone to optimization.
Well, it depends. It allows you to play with it a bit more as well.
Is there a reason, I mean, probably what I've just said, but is there a reason not to just try running all the link statements in parallel all the time?
That really depends on what you're running as the collection. In some instances, if you're running across, if your lists or collections are, say, database objects, and they're running from different data contexts, then potentially yes, you may be better off in a lot of those cases not passing an actual object pulled back from, say, something like Entity Framework directly into a thread to run the operation. You might be better off passing the ID into the thread, and the thread performing the database work to load it into an Entity Framework or object, and then allow you to interact with the object. You will probably find that trying to access that initial object, if you loaded it on the primary thread and tried to offload the task to actually perform work on it, will fail because it doesn't have the context that loaded that object on the same thread that you're running the actual work on. So many of the systems are not designed for that, unfortunately.
Any more questions? Brilliant.
Was it helpful?
Very
helpful.
Are you in a position where there's more questions I can answer in a break or after? Please feel free, come and kick me. Okay.
Thank you.